Very good morning, students. Today I will discuss on CMOS scaling theory that is belong to module 2, and I have already shared the lecture 1 on the based on module 2, that is the introduction of scaling theory, and why we are studying these nanoelectronics and what is the basic fundamentals, where is the applications, and why it is called nano, right? And what is the interrelation between nanoscience, nanoelectronics, and nanotechnology, right? So today I am here to deliver my lecture on the details of CMOS scaling theory, how it is done and how it is scaled and what is the scaling factor, everything. But before goes to that point, that interior point, we have to discuss a lot before entering the scaling part, right? Okay, and I am assuming that all of you have a basic knowledge regarding CMOS, because I have already shared that why the complementary MOS, that means metal oxide semiconductor and Mosfet is used, and why what is the advantage of that, why CMOS is used in nanoscience and nano electronics. So that idea you already have, right? So today I will discuss not so details of CMOS, but I will focus on CMOS scaling theory, right? Okay, so I have written over here that is module 2 lecture 2, because I have already delivered lecture 1 on the based on module 2. That's why I have written over here that is lecture 2, right? Okay, so today's class we will discuss briefly the scaling techniques using CMOS, and I will focus on different kind of materials used in nanoelectronics, right? Okay, so in the previous lecture I highlighted 2 points. One is your materials, and second one is device structure. These 2 points I highlighted many times in the first lecture of module 2. Please remember that why I am focusing on materials and device structures, because these two will play a fundamental role, important role in the CMOS scaling theory, right? Okay, so because we are living in in the year 2020, but 10 years ago, if you ask someone that regarding these material and device structure, the answer was different. But now in today's scenario, there are so much modification, and the answer is also different. In today answer is also different, because new technologies coming out, and new research is going on, so that's why the answer is totally different. So if you ask someone 10 years ago regarding these materials used in nanotechnology, the answer was different, and today's answer is also different. And why it is so? Because there are so much modification and so much changes in these material. Okay, so material will be a very important factor, very important parameter of any nanoelectronics, of any scaling theory also, right? And the materials that is coming out day by day, and the new materials, and from the past materials, where we can see the detailed structure, that is nothing but, yes, you all know this answer, that is the periodic table, right? Because from the periodic table we have the knowledge, we will gain the knowledge from different kind of materials that is coming out day by day, and their properties and their everything, the physical property, chemical property, everything, right? Okay, so from this periodic table we can get a basic idea of regarding these materials, right? So coming to my focusing point, that is CMOS scaling theory and the semiconductor that we have already covered, you must see that silicon is the core semiconductor material, right? Silicon is the core semiconductor material that we have already known, right? And only this is the silicon that is used as a substrate. I have already discussed in the previous lecture. But if you want to increase the conductivity, if you want to increase the conductivity of the device, what technique you will follow? Yes, so the technique will be followed, that is nothing but doping, right? And in the doping there is also material, because which kind of material will be used for doping, whether it is N-type material, whether it is P-type material, and so on. So we have to focus on the material once again. So material is coming to the limelight every time whenever we will talk about this nanoelectronics and scaling theory, right? So for N-type material, you all know a common answer is arsenic, phosphorus, that we have studied from the BTech first year, from the basic electronics, right? But and for P-type, there is two type. One is your N-type, one is your P-type. For N-type, this is arsenic, phosphorus, and for P-type, this is boron. That is our common answer, right? And what kind of material we need? This is all about your substrate making, and this is all about your doping, because we have already seen the structure, that is N plus, N plus, P plus, P plus for any for any MOSFET, whether it is N channel MOSFET, P channel MOSFET, there is two region, that is N plus, N plus, or P plus, P plus. If it is P channel P-type substrate, then it is N plus region, and if it is N channel N-type substrate, then there are two regions, that is denoted by P plus. So why it is called P plus? Because plus means there is a doping, right? Okay, so and most important section, that is the gate terminal, right? And for gate terminal, we have to do the insulation from the substrate, because gate is not directly connected to the substrate. Okay, and please recall the structure of MOSFET for discussing this portion. I am just drawing the very basic part. This is your gate, this is your source, this is your drain, there is a channel. Yes, so this is the portion. So for this kind of substrate, we have used silicon. For this region, for this doping concentration, we have to use doping for N-type, P-type material, and so on. So material is focusing again and again, and one important terminal, that is gate, which is a very important terminal, because without gate voltage we can't do anything on this MOSFET, and gate is not directly connected to the MOSFET. You all know the very common reason of that, because there is a insulation, there is a oxide layer that is acting as an insulation layer between the gate terminal and the substrate. So for this insulation, for this oxide layer, you have to use what kind of material? Yes, you have to use the oxide, that is nothing but the silicon dioxide. I am just giving the example that how the material is becoming an important parameter for any kind of design, because of our subject, that is nanoelectronics. So we will enter the scaling part, but before that, material plays an important role, and that we have to discuss in very detail, right? Okay, so silicon dioxide for gate material, right, and insulation, right? Okay, so once you complete your design, you have to connect these terminals for this metallization part, otherwise you can't do the biasing supply voltage, right? For without metal contact, we can't do that. Okay, so metal contact, what kind of material we will use for this metallization? That is aluminium. It's a very common answer, right? The aluminium. So, and for surface passivation, H2, that is hydrogen, is used as a lighter element. And what is surface passivation? What is your photolithography? What is doping? What is etching? And what is ion implantation? What is diffusion? Each and every process I will discuss in the fabrication module, right? And how we will do this fabrication, how this structure is built up layer by layer, that I will discuss in the fabrication part, and all the process involved that I have just told just a minute ago, that is the photolithography or implantation, and so more processes will be discussed in that section. Okay, and just today now get an idea of how it is going on, right? Okay, and After this metallization, for surface passivation, hydrogen is used as a lighter element. Okay, and whenever we go from one layer to another layer, there may be some defects, and that defects are eliminated by this hydrogen due to this passivation effect. From the word passivation, we are knowing that passively it is doing something. So hydrogen, we will use hydrogen as a lighter element due to its passivation effect, right? Okay, and once it is fabricated, then passivate it silicon nitride before packaging. What is the significance? I will discuss in fabrication chapter. Just get the idea, just gain the idea that how it is going on, because we are only focusing on the materials, and I am here to highlight the materials that is used generally. Okay, so before packaging, for surface passivation, silicon nitride is used. We have to passivate it. Once it is fabricated, we have to passivate it by using silicon nitride. Just gain the idea, not so detail in your syllabus, but you have to know in detail, because you are the communication engineer, device engineer, right? So you have to know you must have the knowledge regarding your semiconductor device, all about nanoelectronics. So you have to study in detail, but there is not so much detail in your semester, in your syllabus, but I think that you have to know in detail. Okay, you have to know detail the syllabus, detail the chapter, detail the nanoelectronics, right? Okay, so that's why I am explaining in very much detail, but there is not so detail in your syllabus, right? Okay, so we have discussed, we have given a very brief idea about the materials, some parts of the device and how it is made of, right? So now world has changed, okay, and completely now you see that there are plenty of materials in the state of that our silicon chip today. Okay, so that we discussed 10 years before, but 10 years after, now we at 2020, we will see that there are plenty of materials are coming out, and that will be used for designing on the silicon chip. Okay, so for example, that how the changes is happening. For example, as doping material, I have already said that arsenic, phosphorus, boron and everything were used, right? But now in today's scenario, I will share the PDF, so not to worry about that. In today's scenario, the doping material is used as your antimony, indium, etc. So it's a new example that was not used in today's, but 10 years or 20 years before. And if you know the metallization part, that I have already said that aluminium was used, but in today's scenario it is used totally based on copper. Is costly, but the cost is coming down due to some effect, due to some process, due to some system, and that will be the next part of the scaling, and that will I will come to that point. But just know that copper is replacing aluminium, right? So similarly, there are many reasons that why we introduced a variety of materials. So there are big exploration of the periodic table that I have already discussed before to really build this nano electronics chip. Okay, so there are variety of materials, and as well as I must say that there are variety of materials, and parallelly the exploration of periodic table, right? So it's a very brief introduction, very brief. Okay, just you have to know the knowledge about that why we are focusing on the material. So an appreciation of the material technology is very much important, and that's why there are various branches are there, the material science, metallurgy, and on that you can do the MTech, you can do the higher studies, only study of the material, which material is suitable, which material is not suitable, which is sustainable, which is reliable, everything. and that is a study, that is a research area in today's scenario. Okay, and you can do that. Your higher studies only on the materials, and so much researches are going on, right? Okay, so now come to the point, come to the next part, that is new device structure. We have already discussed some very basic things and very few things on the materials, and now I will discuss on the new device structure. New device structures are essential. This is my key point and why it is called so. And after that, I will enter the nanoscale effect and then the scaling theory, different kind of scaling. And you will get a very interesting knowledge that due to this scaling theory, how the device becomes faster. We need not any, we need no modification, no redesign of the circuit, but parallelly we are getting a faster device due to this scaling. So it's a very interesting part, and that I will come to that point. But before going to that section, we must discuss that new device structures are essential and how we can say in favor of this point, how we can discuss these points, right? Okay, so we will discuss, that is, we are taking the structure of a FET, that is nothing but source, gate and drain, right? And basically it's a MOSFET, so it's basically acting as a switch. So I must say this structure also. And here I am writing a parameter, that is leakage current, and why it is so I will make clear it to you. Okay, and there is another parameter, that is short channel effect, and that I will discuss. Okay, so why and this is, if I draw in detail, just a minute. This is drain terminal, this is gate, and this is source. This is your short channel effect. This is VD, and this is making ground. So why it is so? Why we are showing this structure? Because scaling means scale the gate length. Okay, scaling means scale the gate length, and if what is the gate length? This is nothing but the distance between the source and drain terminal. So scaling basically means that reducing the gate length, and by reducing the gate length, how the new device structure is coming out and why it is so, what is its properties, that will be discussed, right? So here for typically n-channel transistors, source terminal is grounded, and the drain terminal has a positive voltage, that is VD. Okay, and what is happening with this scaling is that this drain terminal and the gate terminal becomes a very closer to each other. Wait, that is very fundamental, no? Because we are reducing the gate length. So by reducing the gate length, the drain and source terminal are coming to closer to each other, and that is called the proximity effect. Okay, so I mean that we need to consider this two-dimensional distribution of the electric field, because we all know that this is a voltage control device, and drain electric field has started influencing over here because source terminal is grounded, because we are discussing the n-channel transistor, right? So this distribution of the electric field are very much important for this kind of device, and based on that the scaling will be done, and the name of the scaling is so closer to the electric field. Okay, so even without the gate being there to turn on the transistor, meaning ideally means without gate we will get ideally zero current. Without, if the gate terminal is not there, we will get a zero current. But in practical, we get a very small current should be out of there, and because of this proximity effect, there will be a leakage current, and it is very harder and harder to turn off the transistor or FET in the dimension of the scaling. So got my point? Okay, because we are again I am saying a very key points what I have discussed, that is we are doing what is we are discussing that scaling means scaling the gate length, right? So scaling the gate length means if we scale the gate terminal, then drain and source becomes a very closer to each other. And if the gate is not there, so here source terminal is grounded, so the positive voltage is VD, that means the drain voltage. So if there is a voltage, there must be electric field, and this electric field will start influencing over here, over what? Over this scaling effect. And based on that, I will discuss the constant field scaling, that I will come to that point. And here the electric field will start influencing over here, and if the gate terminal is not there, we will get a zero current. Very basic thing, right? But we in practical we will not get a zero current, we will get a very small current, and that is known the leakage current. So it is harder and harder to turn off the transistor or FET at the dimension of the scaling, but we have to turn off the device properly, right? So we will focus on two parameters, that is on current and the off current, right? Because we know that the transistor acts as a switch, and we consider the switch, it has a very large on current and a very small off current, right? It should be a very basic thing that any switch must have a large on current and very small off current, and the very important metric of the transistor, based on that, it is I on by I off ratio, is on current by off current ratio. Is a very important parameter, very important metric of any kind of FET or any kind of transistor. And ideally it should be what value? It should be the value of ideal value. What would be the expected value? Yes, your answer is right. The expected value will be, yes, infinity, because I of should be 0 now. Ideally it should be 0, because switch means there is only on current, no off current. So I of is 0, so I on by 0, that means the ideal value is infinity. It should be infinity, right? But you know that we can't get this value infinity. And on to off current ratio, which is in the order of 10 to the power 6. That means on current is million times more than the off current, and which is a very good abstraction of this switch, right? So what we have said, that is the on current and the off current, and the metric is the parameter to define that this is the on current by off current ratio. But ideally this off current should be 0 and this value is infinity, but practically we don't get the infinity value. It's very basic, is very well known, right? So basically this on current is 10 to the power 6 times of the off current, and it is a very good abstraction of the switch, right? And but if it goes to 10 to the power cube, 10 to the power 3 from 10 to the power 6, it will not be a good abstraction of the switch. Then we have to modify something at the channel, because channel is very basic area, very known area through which the carriers are moving for this current. So this can be done by new device structure. Got my point? Again I am saying that this on current off current, it is a very good idea, right? So ideal value infinity, but practical value is not infinity, that we have already discussed. Basically on current will be 10 to the power 6 times of the off current. This is a very good abstraction of the switch. But if it goes down, if it decreases to 10 to the power cube from 10 to the power 6, then we are getting a very small on current. Okay, so this is not a good abstraction of the switch. Then we have to modify something, and modify where? Obviously this is a channel, because through this channel the carriers are moving out, right? So if we have to modify the channel, we have to build out a new device structure, because there is another channel length. We have to modify we have to scale the channel to some factor, whether it is decreasing, whether it is increasing. So you have to do the scaling on this channel. That's why there is a channel length modulation. We have to modify this channel length, and if we do that, we will obtain the new device structure. So that's why I am focusing on 2 points from the very beginning, that one is material and one is device structure. So in order to get a new device structure, you have to scale the device. So what is the need of this scaling? I think that you must have the knowledge now that why we are doing this scaling. We are doing this scaling because of these two factors. So in order to get a new device structure, we have to do the scaling, right? So our next discussion point, that is the nanoscale effect. It's a very important point, right? Okay, so up to this is the very basic needs of your scaling, and in my next lecture I will discuss the nanoscale effect, and along with that what is the scaling factor, how the scaling is done, everything. So please gain knowledge about what is scaling, why the scaling is needed, and in the next lecture I will discuss how the scaling is done. So till then, enjoy this learning.